Edx M3 January 2010, question 7 on elastic strings and stored elastic potential energy. Pause the video, have a good read of the question and resume the video when you're ready to continue. Here's the first part then, and I've drawn the diagram. A particle is effectively dropped, released from rest at A, drops down, and we've got to find an expression for v squared when the extension is x. So fairly standard bookwork here. It's a conservation of energy. We've got GPE goes to elastic potential energy plus kinetic energy. GPE equals EPE plus KE. So for these 4 marks, all we have to do is put the terms in. The gravitational potential energy at the top is mgA plus x, that's the height difference, a plus x, is equal to 3 over 2 mg, that's your lambda, x squared over 2a, plus a half mv squared. And that's the energy equation done. We almost got our 4 marks, we've just got to now divide by m, double everything, and tidy things up, collect the terms up, and that will give us the expression they've got there. And that's your 4 marks for that part of the question. As far as the mark allocation is concerned, there was a method mark for using the energy equation and an accuracy mark for getting the answer they wanted, and then 2 accuracy marks for getting the terms in the 2 accuracy marks, I beg your pardon, for getting the correct terms in the correct places in the energy equation. Next part of the question. The greatest speed attained as it falls is when the acceleration is 0. Now that's when the tension equals mg. It's as it passes through what would be the equilibrium position. So let's put t equals mg. Okay, let's do that. T equals mg. And we've got mg would equal lambda x over L, which in this case becomes 3 over 2 mg x over a. And that gives us an extension of 2a over 3. So we're nearly there now. We've got the x, we put that back into the v squared expression. X squared, 4a squared over 9. I'll leave you to check that. That when you tidy things up comes to 8ga over 3. That's your v squared, so v is the square root of 8ga over 3. And for that part of the question, there was an M1A1 for this part here, finding the extension when it's got the when the tension equals mg, in other words when it's going at its greatest speed. Right, there was then there was another, that was an M1A1. There's a total of just 4 marks for this. So M1A1, M1 in here, and A1 there. Yep. And the last part of the question. The magnitude of the acceleration when it comes to instantaneous rest. Well, this isn't as bad as it looks. It's 6 marks, so it's quite generous. If it comes to instantaneous rest, v is 0. So putting v equal to 0, this is the expression for v from the first part of the question. Let's put it equal to 0. What happens when you put that equal to 0? You'll get a plus x equals 3x squared over 4a. That gives you a quadratic equation which you can factorize. Again, check these steps yourselves. So the only positive root there is x equals 2a. So that's when it comes to instantaneous rest, x equals 2a. We've got to find the acceleration. Now the acceleration would be measured, would be positive in the downwards direction. So mg minus t equals mx double dot. Mg minus, let's put in the value of t then, 3 over 2 mg z lambda, 2a over a. And that's equal to mx double dot. X double dot being acceleration, as I'm sure you're well used to. So the acceleration x double dot at this point comes to be minus 2g, which makes sense because the acceleration, because the tension, because it's at rest at this point instantaneously and the tension is pulling it back, the acceleration is actually acting upwards, so it's negative in the downwards direction. And for this part of the question, there was M1 for putting v equal 0, M1 for solving the equation, quadratic equation, A1 for getting the correct value of x from the quadratic equation, and then M1 for Newton's law for the acceleration, and 2 accuracy marks for dealing with that properly and getting the right answer. Does that come to 6? 1, 2, 3, 4, 5, 6. That's right. And that's it. Thank you for listening. I hope that was useful.